So in today's lecture, we will continue our remaining parts of the limit of sequence. Okay. So in last lectures, we have seen some example of limit of sequence. Okay. So today we will see another example. So example is prove that the sequence Sn converges to 4 where sequence is defined by n term. The n term is 4n plus 2 upon n plus 5, and we have to prove that this sequence whose n term is this converges to 4 using our general epsilon m definition. Okay. So first step, what we have to do to show that this sequence has a limit 4. We know the definition. Definition is for any epsilon greater than 0, we have to find element m, a number m, such that difference between Sn and that limit L is less than epsilon whenever n greater than equal m. Okay. So the main point is to find this m. Okay. Whenever n greater than equal m, difference between Sn and limit get very much less. Okay, less than epsilon. So here Sn is 4n plus 2. So we directly take the difference. Okay, we know the Sn. What is the value of Sn here? Is 4n plus 2. 4n plus 2 upon n plus 5 minus limit. So we have to put limit is 4. So directly take 4. Okay. Now for 4 to be limit of this sequence, the difference must be less than epsilon. Now the only part, the important here is to find the value of m. Okay. So first we will solve this to get the value of m. Okay. So take the difference. So this becomes 4n plus 2 upon n plus 5 minus 4 times this minus 4 times n plus 5. Okay. So 4n plus 20. Okay. And upon n plus 5. Okay. So just take this subtraction. And this must be less than epsilon. Okay. So now, so 4n plus 2 minus 4n. So 4n minus 4n get cancelled. So here 2 minus 20. Okay. So we get here, this becomes mod of 2 minus 20 upon n plus 5, and this must be less than epsilon. Now 2 minus 20 means minus 18. This applies minus 18 upon n plus 5 must be less than epsilon. But mod of negative number, we take it positive. So taking mod, this becomes 18 upon n plus 5 must be less than epsilon. That is, but we have to find m such that whenever n greater than equal m, so we have to derive this condition. So that purpose, for that purpose, we have to take n on one side. Right? We have to find the value of n is greater than equal some number m. So transfer this denominator n plus 5 to right side. This becomes 18 upon n plus epsilon less than n plus 5. That is, now transfer this 5 plus side. Why? Because we have to only take n to one side. Okay. This applies. Here n plus 5. No? So n greater than, transfer 5 to this side. So 18 upon epsilon minus 5. Okay. So this is the value of n. Okay. Why? Whenever for this to be less than epsilon, n must be greater than this number. So whenever n greater equal this number, difference less than epsilon, so limit of this sequence is this. So we must take the value of m greater than this number. So choose m is greater than this number or this equal to m is equal to this. So choose m is equal to 18 epsilon s naught minus 5. So whenever we take m is equal to this value, then whenever m is greater than this, okay, the difference between, take this. So difference between Sn and L, the difference between this and 4 less than epsilon. So this sequence converges to 4. Okay, whenever we take this value here. So choose m is equal to this. So we get whenever epsilon greater than 0, difference between Sn and limit less than epsilon whenever m greater than equal m. Where Sn is 4m plus 2 upon m plus 5, limit is 4, and value of m is this. Okay. So taking this value, we satisfy this condition. Difference is less than epsilon whenever m greater than equal this m. Okay. So this implies this sequence converges to 4. Okay. Now here is one definition, that is, if limit of sequence exists, then the sequence is said to be convergent, and if limit of sequence does not exist, then sequence is said to be divergent. Okay, so these are the sequence, we can say it is convergent or divergent, depends on their limit exists or not. Okay, if limit exists, sequence is convergent, and if limit of sequence does not exist, then we say that the sequence is divergent. Okay, so now we will see one important theorem. Okay, so the theorem is, if limit of a sequence exists, then it must be unique. Okay, we can say a sequence can have at most one limit. Okay, so whenever a sequence has two different limits, then we can say that sequence does not have a limit or sequence is divergent, because if sequence has a limit, it must be unique. Okay, so sequence cannot have two or many limits of a same sequence. Okay, so we will see proof. So we will prove this theorem by contradiction. Suppose we assume that sequence has two different limits. Okay, so suppose sequence S is defined by Sn has two limits. Okay, say L1 and L2. Okay, so we assume the sequence has two limits, L1 and L2. So what we have to prove at the end? We have to prove that the limits are same. Okay, that is L1 is equal to L2. Now L1 is limit of sequence. So by definition, so since L1 and L2 are limits, so by definition of limit, we can say that for epsilon greater than 0, there exists a natural number m such that whenever m greater than m or greater equal to m, difference between Sn and limit must be less than epsilon. When epsilon is positive number, we can take epsilon by 2 also, epsilon by 3 also. Okay. Now, similarly, L2 also limit. So again by definition, for any epsilon greater than 0, there is a Theorem such that whenever m greater than equal m, difference between here, take here one. Okay, difference between Sn and limit less than that epsilon by 2. Okay, here we can take epsilon by 2. Okay, now here we are taking epsilon by 2 just for adjustment. Okay, now we have to show that L1 and L2 are same. Okay, so for that purpose we will take difference between L1 and L2. Okay, so mod of difference between L1 and L2, okay, is equal to, we will make some adjustment here. Okay, so we add Sn and subtract Sn in this mod. Okay, so this become Sn we are added and minus 2 taken as it is. So Sn minus 2. Okay, now we have added extra term Sn, so we have to subtract this term to maintain the same value of this mod. Okay, so we have taken Sn, so we have to subtract Sn. So this now subtract Sn. Okay, minus Sn, and here take L1 as it is, but we have taken bracket and minus sign outside. So take L1, to take L1 we take here minus L1 by minus minus plus. So plus L1 as it is, minus L2 as it is, added Sn, subtracted Sn. Okay, so I make some adjustment here. Value of this mod and this mod are same. So just added Sn and subtracted Sn. Okay, now we know the triangle law, which means mod of A minus B always less equal mod of A plus mod of B. Okay, so similarly here we can say this is A, this is B. Okay, so by using triangle law, here mod of L1 minus L2, L is as it is. So by using triangle law, this become less equal this. So mod of A minus B less equal mod of B. So mod of A, so mod of first term Sn minus L2 plus mod of second term plus mod of Sn minus L1. Okay, now whenever m greater equal m, this mod and this mod are less than epsilon by 2. So whenever m greater equal m, so this difference, okay, this difference mod of L1 minus L2, this is less than epsilon by 2 whenever n greater equal m. So we take n greater equal m, so this is less than epsilon by 2 as given here. Also this mod also less than epsilon by 2, so this also less than epsilon by 2, that is, and this is mod. So mod of any number always greater equal 0, so we can say that 0 less equal mod of L1 minus L2, and this is strictly less than sum of epsilon by 2 plus epsilon by 2, that is epsilon. So see, this mod greater equal 0 and strictly less than arbitrary number, so we can take epsilon as very small number, 0.01, 0.001. There are infinitely many terms we can take as epsilon. Okay, we can take epsilon as very close to 0, that is 0.0001. So any number which is strictly less than any arbitrary number and greater equal 0. See here, we can take epsilon very small, which is 10 into 0. So number which is greater equal 0 and less than a very small number, there is only one option remaining, that is this must be 0. Okay, this implies the difference must be 0, that is L1 minus L2 must be equal to 0. This implies L1 is equal to L2. Okay, so this implies a sequence has at most one limit, or if limit of a sequence exists, it must be unique. Okay, so friends, you will see one important conditions for limit of sequence. See, if Sn is a sequence and we have derived two subsequence of Sn, one is sequence of even terms, okay, S2n, and other is sequence of odd terms. Okay, for example, we have given sequence of natural number 1, 2, 3, 4 up to so on. So collect even position terms in one set, in one sequence, and collect odd number positions element in other sequence. Okay, so example, then 2, 4, 6 will become one subsequence, and 1, 3, 5, 7, 9 becomes other subsequence. So these are the two subsequence, and find limit of each subsequence S2n and S2n plus 1. If both have same limit L, then the original sequence Sn is convergent and also has a limit L. Okay, that is the limit of s to n subsequence and limit of s to n plus 1 subsequence has the same limit equal L, then limit of sequence Sn also L. Otherwise, if the two subsequence S2n and S2n plus 1 have different sequence or they have no limits, okay, either they have different limits or limit of this subsequence does not exist, then limit of sequence Sn also does not exist. Okay, suppose limit of S2n is 1 and limit of S2n plus 1 is 2, both have different limits, that is 1 is not equal to 2, so original sequence Sn does not have limit. Okay, now the next important here is a convergent sequence of real number is always bounded. Okay, so take any convergent sequence, it must be bounded, that is, if sequence is not bounded, it is not convergent. Okay, so a convergent sequence of real number is bounded, that is, for sequence to be convergent, it must be a bounded sequence. Okay, but if sequence is not bounded, it doesn't have a limit. Okay, so we will see the theorem. Okay, so we have given a convergent sequence. So let xn be a convergent sequence. What is my convergent sequence? That it has a limit. So say the limit of this sequence xn is x. Okay, now we have to prove that this sequence is bounded, that is, each term is less than some number. Okay, so we have to prove that mod of xn is always less equal some number a. Okay, now we are given a sequence xn converges to x, then use the definition, that is, for any epsilon greater than 0 there exists m such that whenever n greater than equal m, difference between n term and limit less than epsilon. Okay, now mod of xn, we will make some adjustment, is equal to, just add and subtract one term. We know value of this mod, so subtract x and add x. Okay, see, mod of xn, we have just added one number x limit and just subtracted this limit. Okay, so LHS and RHS becomes same. Just some adjustment here. Again we know triangle law. Suppose this is A and this is B. So mod of A plus B always is equal mod A plus mod B. Triangle law. Mod of A plus B always is equal mod A plus mod B. So suppose this is A, this is B. So by triangle inequality, this is always less equal mod of xn minus x plus mod of x. Okay, so this is by triangle inequality. Okay, now we already know this value is less than epsilon, so mod of xn is less equal. Okay, mod of xn minus x, which is strictly less than epsilon, so this becomes strictly less than epsilon plus mod of x. But whenever n greater equals m, okay, whenever n greater equals m, so all the terms of the sequence xn are less than this number whenever n greater equal m. Okay, but what about the elements when n is less equal m? So all the terms whenever n greater equal m of the sequence are less than these terms. But what about terms where n is less equal m? For example, see, suppose xn is the sequence defined by n term 1 by n. So first term is 1, second term is 1 by 2. Third term is 1 by 3. Okay, up to so on. Now see, if we take m is equal to 3. Okay, so after third term x3 is equal to 1 by 3, then 1 by 4, 1 by 5 up to so on. The terms goes on increasing. So take m is equal to 3. So whenever m is equal to 3 and we have to take n greater equal m. So whenever n greater equal 3, why? Because m is equal to 3, all the terms are less than 1 by 2. See, 1 by 3 is less than 1 by 2, 1 by 4 is less than 1 by 2, and all the terms are less than 1 by 2. So whenever m greater equal m, where m is 3, the terms are, all terms are less than 1 by 2. So we can take less than 1 by 2. The same here, all the terms of xn are less than this number, whenever m greater equal m, But what about the terms? We have taken here terms from x3, x4 up to so on. But what about x1 and x2? Here n is less equal 3. So we have derived condition that mod of xn is less than 1 by 2 whenever n greater equal 3. But what about n is equal to 1 and n is equal to 2? For n is equal to 2, x2 is equal to 1 by 2, and for n is equal to 1, x1 is equal to 1. So each term of xn is less than 1 by 2 whenever n greater equal to 3. Now only two terms left, x1 and x2, which are 1 by 2 and 1. So we can say the maximum value of these three is the upper bound for xn. See, mod of xn, each term less than 1 by 2. After this, n is greater equal to 3, and for n is equal to 1 and n is equal to, these are the values. So each term of xn is less than 1. Why? Already all the terms are less than 1 by 2. n greater equal to 3. Second term is 1 by 2, and third term is 1. We can say less equal 1. Okay. So second term is 1 by 2, first term is 1, and all other terms are less than 1 by 2. So each term is less than 1. Okay. So first two terms are 1 and 1 by 2, and other terms are less than 1 by 2. So highest term in this xn is 1. So all the terms are less than 1. This fact we have to use here. Here all the terms whenever n greater equal m are less than these numbers. So what about previous terms? Here all terms whenever n greater equal 3 are less than this number. But what about n less equal 3? What about n less equal m? So take the value of n is equal to 1, n is equal to 2. We get these two values, and maximum of these three values, here 3 is the maximum value, upper bound for xn. So similarly here mod of xn is less than this element whenever n greater equal m, and just take the other values whenever n less equal m. So maximum of this is the our required a. Okay. So now we will find out the value of terms of n whenever n less equal m. So from this condition we see that the element of the sequence xn whenever n greater equal m are less than this term. But what about the element where n is less equal m? So for that purpose we take a is equal to maximum of mod of x1, mod of x2 up to mod of xm minus 1. Okay. Now ahead of these terms, that is from xm, xm plus 1, xm plus 2 up to so on, all the terms are less than this element. Okay. And so we write here epsilon plus mod of x. Okay. Why? Because the terms from xm plus 1 up to so on are already less than this. See here, whenever n greater equal m, mod of xm is less than this. So we have to only think about previous terms like mod of xn, mod of x2, mod of x3 up to mod of xn minus 1. So maximum of these terms we take a. So we get from this mod of x1, mod of xn always less equal the term a, where term a is nothing but either these terms or this term. Which is maximum among these terms? Nothing but a. This implies sequence xn is bounded. So we have taken a convergent sequence and we have shown this sequence is bounded. Okay. So every convergent sequence of real number is always bounded. So here xn is bounded. Okay. You understand why we taken a here? Because each term of xn from xn plus 1 is less than these terms. So if this is maximum, this is the upper bound for xn, or among these terms, whoever maximum is the upper bound for xn. So xn, mod of xn is less equal a, so xn is bounded, and we have taken xn as a convergent sequence. So every convergent sequence is bounded. Okay. Now we will see some example of sequences. Okay. Here are some sequences, out of which some sequences are bounded and some sequences are unbounded. Okay. Now this sequence here whose n term is 1 by n. We have already shown that this sequence has a limit 0 using epsilon m definition. Okay. Now we can also show the subsequence of the sequence Sn, where first subsequence is s twice n. That is a subsequence derived from Sn by taking even position elements. For this subsequence, n term is 1 by twice n, and we can easily see that as n tends to infinity, 1 upon twice n tends to 0. So this subsequence s to n has a limit 0. Similarly, subsequence derived by taking only odd position elements has n term 1 upon twice n plus 1. Also as n tends to infinity, 1 upon twice n plus 1 also tends to 0. So this subsequence s twice n plus 1 also tends to 0. Also has a limit 0. So both subsequence s twice n and s twice n plus 1 has a limit 0. This sequence Sn has a limit 0. Okay. Now next sequence Tn whose n term is minus 1 raised to power n. Now see, we will take subsequence sequence of even position. So first we will try to list the element of this sequence. Put n is equal to 1. So T1 minus 1 raised to power 1, which is minus 1. Take n is equal to 2. So the second term T2 square of minus 1. So plus 1. Third term cube of minus 1 minus 1. Fourth term 4 power of minus 1 plus 1 up to so on. So see here we can see that T2n, that is sequence of even position, is here subsequence of even position is 1, the second position even 1, fourth position 1 up to so on. So this sequence is constant sequence and each term is 1. This is our T2n and it has a limit 1. Why? Each term is 1. So constant sequence has a limit that number 1. Okay. And other subsequence which is obtained by taking the element at odd position. So first position, third position, fifth position up to so on. So T twice n plus 1, which is equal to minus 1 up to so on. This is also constant sequence and each element is minus 1. So this sequence, this subsequence converges to minus 1. Okay, that is T2n converges to 1 and T twice n plus 1 converges to minus 1. So limit of Tn is equal to, see if n is even, limit is 1. If n is odd number, limit is minus 1. So limit of Tn is 1 if n is even and it is -1 if n is odd. C. Sequence has two different limit depend on value of n. When it is even, when the limit is 1, when it is odd, limit is -1. But we know if limit of sequence exists, it must be unique. So this sequence -1 raised to power n is divergent, does not have a limit. But its subsequence has a limit. The even position subsequence has limit 1 and odd position subsequence has limit -1. But sequence Pn is divergent, okay? Because limit does not unique. Okay. Now third sequence un defined by n term, which is n. The element of this sequence are 1, 2 up to so on. Sequence goes to infinity up to so on. So we put n is equal to 1, then put n is equal to 2 up to so on. This sequence is not bounded. Okay. So this sequence cannot be convergent. Why? We have already seen the theorem. A convergent sequence of real number is always bounded. So for sequence to be convergent, it must be bounded. Here sequence is not bounded, so sequence cannot be convergent. Okay. So unbounded sequence not convergent, that is divergent. Again, sequence Vn defined by n term is -n. So element of this sequence are put n is equal to 1. So minus of 1, minus of 2, minus of 3 up to so on. That also goes to -infinity. This sequence also not bounded, so it is also divergent sequence. Okay. So both these two sequences are unbounded, so are divergent. Okay. So this is another sequence Wn. Okay. So we will try to list the element of this sequence. Here n term is n minus 1 raised to power n. So for first term, put n is equal to 1. So we get 1 into minus 1 raised to power 1. So minus 1. Put n is equal to 2. So 2 into square of minus 1. So plus 2. Put n is equal to 3. So 3 into cube of minus 1. So minus 3. Similarly, next term is 4 minus 5 up to so. See here, if we take the subsequence of even positions, so 2, 4, 6 up to so on, the subsequence W twice n is 2, 4, 6 up to so on. They are also not bounded and also tends to infinity. So W2n also tends to infinity. Also, the subsequence of odd positions. Okay, W twice n plus 1. The subsequence has the element -1, -3, -5 up to so on. So this subsequence also tends to -infinity. Okay. So both subsequence of this sequence are divergent. So original sequence must be divergent. Okay. And this sequence also not bounded. Okay. It also unbounded sequence. So these three are unbounded sequence. These two are bounded sequence. But this is bounded and convergent. It is bounded and divergent. Here are unbounded sequence, so they must be divergent.